Today we are again, we'll continue the last lecture, which was about training these neural networks or these CNNs. And we started with like the general idea how we are going to train these networks. And then we talked about the optimization algorithm, that is the stochastic gradient descent. So today we'll continue on that, and the next segment will be backpropagation. And again, this is like a very, I would say, a broad topic. It will take a lot of time, so we'll just touch upon the basics of what backpropagation is and how it plays a role in training on networks. Now, before starting that, let's do a quick recap of what we did in the last lecture. So we were talking about optimization, and given a function, the idea is we want to find a place in this function or the response of this function where the value of this function is minimum. Okay, so that's like a high level idea of what optimization is. And in our case, this function is the loss function. All right, so the loss function which we will write, which will tell you how good your network is performing. Okay, and that we will do because we have the network's prediction and we have the ground truth. So we'll make comparisons and we'll formulate some kind of function which will say, okay, this is the loss value and how this is like how good the network is doing. This is how bad the network is doing. So that's the loss function in our scenario. And the idea is we want to find like these minima points because we want to minimize the loss. Okay, we want like the prediction of the network to be as close as the ground truth. If that's the case, the best case scenario is your loss will be 0. Okay, if your network is actually performing perfectly. So that's the high level idea. We want to minimize that function. And as we discussed, like that loss function is never going to be like a simple convex function. You might have a lot of minima there. In this case, this is again a simple one-dimensional function. It has two different minima. So one at this point and one at this point. So these are called local minimas. So usually like the loss function for neural networks, it will be very complex. So we'll have a lot of minimas and hardly there will be like a global minima. Okay. Now, the idea is we want to reach to this point, and as we discussed in the last lecture, we are going to make use of stochastic gradient descent. The idea is we initialize like our network randomly, which means that the initial prediction will be random. So with that random prediction, the loss value will be high because it will be just a random guess. All right. So in this case, let's say you initialize your network with A1. Your loss value will be something like this because that's your loss curve. And the goal is we want to move this point in this direction and reach this point. Okay, so then your loss value is actually reducing from this level to the minimum level. And your network parameters are actually going from A1 to A stop. Okay, so to go from this point to this point, this is the simple equation, which is like a single step of your gradient descent algorithm. And as we discussed last time, there are a couple of parameters here. The first is, you can look the second term here. This is just computing the gradient. Okay, so we'll find the gradient at this point, and that will help you determine like which direction you want to go, whether you want to increase the value or you want to decrease the value. Okay, so you will use the gradient, and then you have another hyperparameter, which is gamma over here, which is the learning rate. It will control how fast you want to move in either of these directions, either left or right. Okay, so this is kind of trying to control the step size as you move from A1 to A2, A3, and A stop. And eventually, if your value is not changing, because in this case, the gradient will be almost 0. So if you're not changing, that's the stopping criteria. And you say, okay, you have reached the local minimum. And that's when your training ends. Okay, so that's the high level idea. Now, to be able to do so, you know that we were using that simple equation that was like a one step for gradient descent. So to make that one step, we need to compute the gradient. Okay, which means that whatever like functions you have like in your network, you should be able to find the derivative of those functions. Okay, so this is a very important point. So let's start from the end where you have the loss function. Okay, so first of all, you will have to find derivative of your loss function with respect to the parameters. to be able to find that gradient. And to be able to do that, your loss function should be differentiable. And as you know that not all functions are differentiable. So you'll have to come up with a loss function, which is actually differentiable. Okay, not just that, as you move further down in your network, because you are going to find the gradient of your loss with respect to those parameters, which means that everything inside your network should be differentiable. And that's the only way you will be able to find those gradients, because you can't differentiate like discrete functions, right? So which means like you have activation functions in your network, they should be differentiable. You are using the convolution operation or the correlation operation when you are actually moving from layer to layer using that filtering operation, right? So that operation should be differentiable, and we know that convolution or correlation is differentiable. Okay? It's just like linear combination of those pixel values. And any other operation you are performing inside your network, for example, you are performing pooling, that should be differentiable. We know that max pooling is differentiable. And that's one of the reason, if you remember, like when we were talking about filtering, then we came around one very interesting filter that was median filter. And we saw that it was performing pretty well. It was able to get rid of all the noise in the image, right? And the issue is that median operation is actually not differentiable. So that's one of the reasons why we can't use median filtering in our neural networks. And again, that's just one reason. In computational complexity is the other main reason. Okay, so the bottom line is, when you design your network, everything you are using inside your network, it should be differentiable. You can't just plug in like any non-differentiable function inside your network. All right. Now the question is, the gradient descent algorithm I showed you, that was a very simple function. It was dependent upon like maybe just one variable. So it's easy. You can just compute derivative of that function with respect to that variable. But the neural networks are a little more complicated, right? It's not just one variable and one function. It is actually a chain of functions. So if we start with the first layer, if you treat that as a function, then input to that function is your input image, let's say, or whatever input data point you have. And again, that's going to give you some output. So that output is again going to be input for your next layer. So if you treat like each of these layers as functions, so essentially it's like a chain of functions, right? Where output of one of the function is actually input to the next function. And eventually, like at the end, the output of the network is actually going to the loss function as input. And for loss function, you have two inputs. You have output of the network and you have the ground truth. Okay. So, but that output of the network, it's actually coming from a chain of functions. But basically, if you just combine all of that, the basic input is your image. All right. So now if you have all those functions, so to be able to compute derivative for all those variables, you will have to make use of this chain rule. And this is again coming from your high school maths. So the simple chain rule says, if you have, let's say, this function L, and you want to compute derivative of this function with respect to any variable X, and the assumption is this function actually depends on this variable X. So if you want to compute this partial derivative, what you can do is, you can compute the partial derivative of this function with respect to any other variable Z. Again, the function is dependent on this Z. And then you can compute the partial derivative of Z with respect to X. Okay, so this is the chain rule all of you must know. So this is just a recap. Now, if you try to think about the neural network, then if let's say X is like some variable inside your network, and then again, that variable is connected to Z, and then Z is actually connected to the loss function, right? So if you want to compute the derivative of like some kind of intermediate variable or your weight in your network, so you can actually make use of this chain rule. And again, this is just one step. Of course, you can go like deeper. You can have like multiple chains here because your networks will be like very deep. Okay. But however deep it is, mean you will still be able to find this partial derivative. And this is called like a simple chain rule. And this is what is used to compute the derivatives for like a loss function with respect to all the variables in your network. Okay, and this is actually used for backpropagation. So let's first try to understand what a backpropagation is. Let's say this is a very simple neural network. Okay, and we don't know like how many layers it has. It could be just one neuron. It could be multiple layers. But whatever it is, we can represent that in form of a function. Let's say the input to this is x and y. So it will be a function. It will be a function taking x and y as input, and it's producing an output z. Okay, so this looks like maybe it could be a simple neuron, which is dependent on these two variables. Okay, so now if this z is actually being used to compute the loss function, then what you can do is you can first compute the derivative of the loss function with respect to z, which is easy because this z will be like used in the loss formulation, right? You can just use derivative equations to compute that partial derivative. And once you have that, then the goal is to actually find partial derivative with respect to x and y for the loss function, right? So then you can simply use this chain rule. So what you can do is you can first find the derivative with respect to z, right? Which we can easily do here. And then in addition, you'll have to find the partial derivative of z with respect to x. Okay, and again, we can do that because we have this function. We know what this function is. Now the idea is, if you remember like the gradient descent algorithm, you were finding that slope, and that was a loss curve, and the x-axis was different parameters, right? So what we do, we find that derivative with respect to all the parameters we have in our network. And since we can compute that using this chain rule, we can actually take that step, whatever like that gradient step we discussed, which was making use of the learning rate and the gradient. So that step is actually performed for all the parameters. And since you have the derivatives, you know the learning rate, you can easily update the weight value. Okay, so that's actually done for all the weights in all the layers. Okay, so that's how the network is being trained, and propagating these gradients backwards, like from the loss function all the way up to the input. This process is called backpropagation. Okay, this is also called like backward pass. And the other is like the forward pass, where you have the input, you use this function to get the output value. Okay, so that's the forward pass. And to compute, you first compute the derivatives. In fact, like the backward pass is something you actually update the values of the weights using the gradients which you have computed in this step. Okay, so when you train your network, these are the two things which is happening in each step. All right, so that was just one neuron. As I said, like your networks will be like deeper and deeper, but again, you can use the same chain rule. You can just expand those, and it's just showing that because you can compute the derivative for each variable here, right? Whatever variable you have for this layer, and then again you can just keep backpropagating by computing those partial derivatives. Okay, so some simple rules like which are used. So if you are actually adding two different values as a function, then what will happen? The gradient will distribute. So it will act as a gradient distributor, which means that whatever gradient is coming from the top, that will go equally to both the variables. If it's like if the operation is x plus y. Okay, and you can think about, because it's just a derivative, right? So if you compute derivative of x plus y, it doesn't matter. I mean, the derivative has to go to both. Okay, so that's one thing. And so if you have like the max operator, which you use for max pooling, right? So in this case, what will happen is it will act as a gradient router, because when you perform max pooling, only some of the values will be passed to the next layer, right? Others will be ignored. So if others are ignored, then it means those values are actually not influencing the output. So they're not dependent. So the gradient will be zero. So the gradient will not flow back in that direction. So whatever value was used for that max operation, gradient will just route in that direction. Okay, so it's a gradient router. And for multiplication, the gradient will switch. And again, this comes from like the simple gradient rule. If you have x times y, if you compute the partial derivative, if you compute partial, let's say you have an equation x times y, and you want to compute a derivative of L with respect to y. So then y will be just gone, right? Because it's just linear, and you will just have x. And that's why the gradient will switch. If it's Y, it will go to X. And if it's coming from X, it will go to Y. Okay, so just basic, don't worry too much about this. You won't have to like write any code or anything for this. These are just simple basics. Okay, so now what we do is we don't use gradient descent directly like on the whole data set because the data set is too big. And as you know that you need like a lot of images, like millions of images to train your model. So if you try to compute like the gradient or the loss function for the whole data, it will be very, very time consuming. Right, so what we do is we use like a variation of that, which is called stochastic gradient descent. And the idea is you select like a few samples from the data set and you compute loss for those fewer samples. So that's called a mini batch, or you can say a batch. And then you perform this training. Okay, so we randomly sample like a data point. So again, this is stochastic. We just do for 1 point, but ideally we don't do for 1 point. We take like a bunch of points, which is again called not stochastic. You can say that mini batch gradient descent. All right. So, and that is also called the batch size. That's like the amount of the number of samples you're actually using to train your model. And this is one of the hyperparameter. And it actually plays a very important role, like how good your training will be. So like a very big batch size will improve your training speed, but it might not be very good for the performance. And again, if you have a very small batch size, let's say as small as 1, because you are making those updates for each sample, it's going to take a lot of time. Okay, so the idea is, so this is like a very simple training process, how it works. You first of all initialize like all the network weights randomly, and you will have some kind of learn rate. Again, it's a hyperparameter, you will choose it. And then while your loss is not like the minimum one, you will continue your training. Okay, so that's, let's say, your stopping criteria. You can have other stopping criteria as well. For example, you said, okay, we'll train the network for these many iterations, or you can say like we'll train for these many days or these many hours. You can have lot of different variations there. So you will have some criterion to stop. Then what you will do is you will randomly shuffle your training set. Let's say you have 100,000 images. That will be a long list. You will randomly shuffle that list, and then you will start from the top. And let's say your batch size is 16. You will select like the top 16 images, and then you will feed forward those 16 images through your network. For each image, you will have some prediction. You will have the ground truth. You can compute the loss. So you will do that for all the 16 images, and you will just average that loss, right? So that's the loss for that particular mini batch, and you will use that loss value to find the gradient for all the parameters or all the weights in the network and update the weights. Okay, so if you think about this, what's happening is you are improving or you are learning your weights depending on only these 16 samples. And so that's called one iteration because you're training your network once. Okay, so that's called like a single step of gradient descent, and you repeat that for all the samples. You will keep sampling next 16 images, next 16 images until you have used all the images in the training set. Okay, so once you're done with all the images, that's called one epoch. Okay, so that's again a term you should know. So one epoch is something when your network has actually seen all the samples in your training set. All right, and then again you repeat. You will shuffle again those images and keep repeating this process. And usually you train for like multiple epochs. And you will, as you are training those on those images again and again, your network will make better predictions because those weights are actually going towards the minimum. Okay, so that's like a high level idea of how the network training works. So this is called like one epoch when, as I said, your network has seen all the images in your training set.